Hey there. Today, we're going to dive into one of the most famous and persistent mysteries in mathematics. It's a problem so simple to state, you can explain it to a child, but so incredibly hard to solve that it has baffled mathematicians for over 80 years. We're talking about the Collatz conjecture. By the end of our video, you'll be able to explain the Collatz process, trace the path of any number, and understand why this conjecture is such a big deal in the math world. So what exactly is the Collatz process? It's a sequence of operations that you perform on a number. Think of it like a game with a very simple set of rules. Here are the two rules. If the number you're looking at is even, you divide it by 2. If it's odd, you multiply it by 3 and add 1. That's it. You repeat this process with the new number you get. The conjecture itself makes a very specific claim. It says that no matter what positive integer you start with, if you follow these two rules, you will always eventually reach the number 1. Let's say that again. It always reaches 1. That's the core of the mystery. This claim, that every positive integer leads to 1, is what we call the Collatz conjecture. Despite being computationally verified for incredibly large numbers, it has never been mathematically proven for all numbers. We're going to see how this process works with some examples, and then tackle a few problems on your own. To really understand this, let's trace the journey of a few numbers. Our goal here is to be able to compute the Collatz sequence for any given starting number. First up, let's start with the number 6. Watch the animation on the screen as we go through each step. We start with 6. Is 6 even or odd? It's even. So we apply our first rule. Divide by 2. 6 divided by 2 is 3. Now 3 is our new number. Okay, our new number is 3. Is 3 even or odd? It's odd, so we apply our second rule. Multiply by 3 and add 1. 3 times 3 is 9, plus 1 is 10. Now 10 is our number. Let's keep going. We have 10. Even or odd? Even, so we divide by 2. 10 divided by 2 is 5. Our number is 5. Even or odd? Odd, so we multiply by 3 and add 1. 5 times 3 is 15, plus 1 is 16. Now we have 16. Even or odd? Even, divide by 2. 16 divided by 2 is 8. Our number is 8. Even or odd? Even, divide by 2. 8 divided by 2 is 4. We have 4. Even or odd? Even. Divide by 2. 4 divided by 2 is 2. And finally, we have 2. Even or odd? Even. Divide by 2. 2 divided by 2 is 1. And there we are. We've reached 1. The conjecture holds for 6. Now you might have noticed something. After we reached 16, every number in the sequence was even, and we just divided by 2 repeatedly. This is a common pattern. Once you hit a power of 2, you're guaranteed to reach 1 very quickly. The real challenge is getting to one of those powers of 2. Let's summarize. For the starting number 6, the Collatz sequence is 6, 3, 10, 5, 16, 8, 4, 2, 1. Our goal of tracing the path for an even number is complete. That was a good example, but what about a number that is odd to begin with? Let's trace the path of another number. Our goal here is to get comfortable with the rules for odd numbers. This time, let's start with 17. The animation will show us the step-by-step process. 17 is odd. So, we apply our odd rule. 3 times 17 plus 1. That's 51 plus 1, which equals 52. 52 is even. We divide by 2 to get 26. 26 is even. We divide by 2 to get 13. 13 is odd. We multiply by 3 and add 1. 13 times 3 is 39, plus 1 is 40. 40 is even. Divide by 2 to get 20. 20 is even. Divide by 2 to get 10. 10 is even. Divide by 2 to get 5. 5 is odd. Multiply by 3 and add 1 to get 16. Sound familiar? Yes, once we hit 16, we know the rest of the sequence will be 8, 4, 2, and finally 1. This shows that different starting numbers can eventually join the same path. So the full sequence for 17 is 17, 52, 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, 1. We've successfully traced the path of another number, this time an odd one, meeting our objective. Let's begin by writing a simple equation on the board. Here is another equation. Notice how it appears below the first one. Now, let's highlight the first equation. Now we will clear all content from the board. That's all for this scene. Okay, it's your turn to practice. Your objective in this scene is to trace a Collatz sequence completely on your own, applying the rules correctly at each step. This is the best way to get a feel for the process. Pause the video and try to find the complete Collatz sequence for the number 9. I'll reveal the solution in a moment. All right, let's go through it together and see if your sequence matches. We'll animate it step by step. We start with 9. It's odd, so we multiply by 3 and add 1, getting 28. 28 is even. Divide by 2, which is 14. 14 is even. Divide by 2, which is 7. 7 is odd. Multiply by 3 and add 1, which is 22. 22 is even. Divide by 2, which is 11. 11 is odd. Multiply by 3 and add 1, which is 34. 34 is even. Divide by 2, which is 17. 17 is odd. Multiply by 3 and add 1, which is 52. 52 is even. Divide by 2, which is 2x. 26 is even. Divide by 2, which is 13. 13 is odd. Multiply by 3 and add 1, which is 40. 40 is even. Divide by 2, which is 20. 20 is even. Divide by 2, which is 10. 10 is even. Divide by 2, which is 5. 5 is odd. Multiply by 3 and add 1, which is 16. 16 is even. Divide by 2, which is 8. 8 is even. Divide by 2, which is 4. 4 is even. Divide by 2, which is 2. 2 is even. Divide by 2, which is 1. And there you have it. The sequence for 9 is 9, 8, 14, 7, 12, 11, 4, 17, 26, 10, 40, 20, 10, 5, 16, 8, 4, 2, 1. If you got that right, you're in great shape. You've successfully traced a Collatz sequence, accomplishing our objective for this scene. Let's try another one, a number that's odd to start with. This will reinforce our understanding of the odd rule. For your second practice question, try finding the Collatz sequence for n equals 19. Pause the video and give it a shot. Okay, ready for the solution? Let's walk through it, starting with 19. It's odd, so 3 times 19 plus 1 equals 58. 58 is even. 58 divided by 2 is 20. 29 is odd. 3 times 29 plus 1 equals 88. 88 is even. 88 divided by 2 is 44. 44 is even. 4 divided by 2 is 22. 22 is even. 22 divided by 2 is 11. 11 is odd. 3 times 11 plus 1 equals 34. 34 is even. 34 divided by 2 is 17. 17 is odd. 3 times 17 plus 1 equals 52. 52 is even. 52 divided by 2 is TC. 26 is even. 6 divided by 2 is 13. 13 is odd. 3 times 13 plus 1 equals 40. 40 is even. 40 divided by 2 is 20. 20 is even. 20 divided by 2 is 10. 10 is even. 10 divided by 2 is 5. 5 is odd. 3 times 5 plus 1 equals 16. 16 is even. 16 divided by 2 is 8. 8 is even. 8 divided by 2 is 4. 4 is even. 4 divided by 2 is 2. 2 is even. 2 divided by 2 is 1. Great work. The sequence for 19 is 19, 58, 29, 88, 44, 22, 11, 34, 17, 52, 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, 1. If you got that one too, you're becoming a Collatz pro. For our final practice question, let's look at another odd number that will have a slightly more complex path. This is a good test of your sequencing skills. Your objective is to find the full Collatz sequence for n equals 21. Pause the video and trace the journey yourself. Okay, let's check your work. Here's the solution. We start with 21. It's odd, so we multiply by 3 and add 1, giving us 64. Now, you might have noticed something. 64 is a power of 2. Any number that reaches a power of 2 is on the fast track to 1. The rest of the sequence will be 32, 16, 8, 4, 2, 1. So, the complete sequence for 21 is a relatively short one. 21, 64, 32, 16, 8, 4, 2, 1. This demonstrates that even with an odd starting number, the sequence doesn't always have to be long. Sometimes you get lucky and land on a power of 2 early. You've now completed another practice problem and achieved our objective. So, we've walked through the rules and seen several examples. But why is this so special? Our objective now is to understand the significance of this problem in mathematics. The beauty and frustration of the Collatz conjecture lie in its simplicity. The rules are easy, but predicting the path of a number is almost impossible. There's no known formula or shortcut. This problem represents a deep challenge. Mathematicians are looking for a proof that works for all possible starting numbers, but nobody has found it yet. A proof would show that no matter what number you pick, it's impossible to get stuck in a loop, and it's impossible for the numbers to just grow infinitely. Solving this conjecture could reveal fundamental insights into number theory, computational theory, and the very nature of predictable versus unpredictable systems in mathematics. It shows how simple questions can lead to incredibly deep and complex problems. In essence, the Collatz conjecture serves as a humbling reminder of the vast and unknown territories that still exist in mathematics, even in areas that seem to involve only basic arithmetic. We've now fulfilled our objective of understanding its significance. Let's quickly recap what we've learned today. Our goal was to be able to explain the Collatz process, trace a sequence, and understand why it's so important. First, we learned the two simple Collatz rules. If a number is even, you divide it by 2. If it's odd, you multiply it by 3 and add 1. Second, we explored the conjecture itself, which proposes that this process always leads to the number 1 for any positive integer you choose. We traced the sequences for 6, 17, and 7, and you practiced with 9, 19, and 21. We saw how some paths are short and direct, while others like to 7, can be a wild ride before finally falling to 1. And we finished by discussing why this problem is such a big deal. It's a simple idea with profound implications for the nature of numbers. It's a mystery that has yet to be cracked, and it's a testament to the enduring power and beauty of mathematical puzzles. Thank you for joining me today on this journey through the Collatz conjecture. Keep exploring, keep questioning, and maybe, just maybe, you'll be the one to solve this decades-old puzzle. See you next time.